Are you tired of never-ending, unexplained errors in your Excel spreadsheets? Looking for a better alternative? Or maybe you're overwhelmed by the sheer number of programs used in the engineering industry. What are the best tools to do calculations, process data, and ideally spit it all out in a report-like format? In this video, I'll show you why Python is the best tool for structural engineers. I want to focus on 7 key reasons. Replicability, clarity and control, it's free, Python has powerful libraries, flexibility, it's in line with industry standard, and it's future-proof. Reason 1. Replicability. When I joined my first consultancy, hand calculations were still the norm. Don't get me wrong, every engineer should know how to take a pen, paper, and calculator to carry out the design. That's how I did it at university, that's what I did for my chartership exam, but for everyday design, I find it deeply inefficient. The reasons are twofold. Firstly, it's punishing. Make a mistake early on and you're restarting from zero. If you're a slow writer like me, it's incredibly frustrating. Secondly, these calculations are highly replicable, meaning you could reuse them on another project. And we all know what happens when the client requests changes. I've seen the same steel I-beam calcs done from scratch for different sections. Why waste time? Each set of calcs can take a while, at least for me. The first time you do a calculation, you should absolutely do it carefully. Replicate a worked example, understand the engineering behind it, but why not write it from the beginning in a program like Python to automate your process? Reason 2. Clarity and control. Many of you work with spreadsheets. I did too, heavily. I created massive spreadsheets to automate complex calculations, but I found that the bigger the file grew, the less control I had. Tracking cells referencing other cells across different sheets became a nightmare. Where was that one number coming from? Python is different. Code is just text. Your logic is laid out line by line. Anyone can read it, review it, and check your assumptions. No more hidden formulas. The syntax was designed to be read easily. Just by looking at the code, you know what is happening, and you can aid the reader further by adding comments. Jupyter Notebook, in particular, is a powerful tool. You can create a report-like structure and supplement your calculations with non-code cells that include text, images, and even LaTeX formulae. Python gives you back control. For instance, when I see this, honestly, I have no idea what is happening. Excel's loose referencing scatters logic across cell addresses, named cells, ranges, and text strings. Some values come from hidden helper cells, others from another sheet entirely. You end up reverse engineering not just the formula, but the layout of the workbook itself. It becomes extremely difficult to understand what the equation actually means. Okay, let's take something easier. You might figure out it's meant to be a lookup table, but it's not very readable. What is B2? What's in sheet 1? What value am I even getting? Let me translate. Cell B2 contains the material type timber, and this formula is supposed to find that material in sheet 1 and return the corresponding stiffness from the second column. In Python, the equivalent code using a dictionary looks like this. First, I define the dictionary, where material names are keys and the corresponding stiffness is the value. Then I query the key, here timber, and print the output. Using descriptive variable names makes the code far easier to understand compared to ambiguous cell references. Isn't that clearer? Okay, but what if you can't find where the dictionary was defined? Most IDEs let you click on any variable and jump straight to its definition. Try doing that in Excel. I particularly dislike how Excel handles errors. Everything executes simultaneously, globally. If there is an error in one cell, it propagates to every cell that depends on it. Tracing the origin of the error? Good luck. Why are these values not calculated? What are these hash values next to MCR? If there's an error in Python, the code execution stops and the error message tells you exactly what the issue is. Try to divide by 0, Python tells you, here's the error and here's the exact line. Your IDE might even underline the culprit code for you. As your logic gets more complex, The nature of Excel cells pushes you into creating unreadable, monstrous formulas. It's so error-prone. Python doesn't force you to squeeze everything into one line. You can partition your code to make it more readable. For instance, to return the yield strength reduction for steel grade S355 given a plate thickness, you could write several simple if-else statements. Alternatively, you could use something more sophisticated like a data frame lookup table. Fitting such code in a single cell is just messy. To me, spreadsheets can become unreliable black boxes, difficult to follow even for the person who built them. I'm not here to criticize anyone using Excel, I used it for years. But maybe try Python, you might find you like it more. Reason 3. It's free. Python is open source. Anyone can download it on any operating system, completely free. MATLAB, Microsoft Office, MathCAD are all paid programs. At university, I enjoyed using my student version of MATLAB. But the consultancies I worked for? No license. That is never a limitation with Python. Wherever you go, whatever company you join, you will always be able to use it. Reason 4. Powerful libraries. There are countless advanced libraries developed by others so that you don't have to reinvent the wheel. Because Python is open source, there is a big community of developers to maintain useful packages. For instance, NumPy for matrix calculations, Pandas for table-like data, SymPy for symbolic equations, and, in my opinion, the most important, Matplotlib for graphs. Yes, Excel can handle most of these operations, but is typically clunky. Take a simple case of inverting a stiffness matrix and multiplying to calculate displacements. In Excel, you need to carefully drag your cursor to define matrix bounds and hope you didn't miss a cell. In Python, I can define the matrices explicitly and get the displacements in a single line. Excel is also notorious for producing garbage graphs, wrong axis, missing data, or strange formatting. With Matplotlib, you can easily control every aspect of your graph: axis limits, labels, grid lines, and annotations. It ensures consistent formatting every time. And there are even structural engineering packages like Pinite and OpenCSPy. What if you build something useful? You can publish it on GitHub for others to use. Reason 5. Flexibility. There is almost no limit to what you can do in Python. It's a great tool not just for calculations, but for pre- and post-processing data. For instance, if you're working with programs like Adaptive or LSDyna that take scripted data files as input and spit out more text files, Python is perfect for that. You can write a script to prepare the input, here's a simply supported beam model being generated for Adaptive, run the analysis, then take the output file to extract and process the results. Try doing that in Excel. The moment you need to do something more advanced in a spreadsheet, you're reaching out for macros. And macros are essentially scripts, but with strange limitations. When I used them, I constantly encountered problems, and overcoming them, that required workarounds that felt just like fighting the tool instead of using it. Python doesn't fight you, it just works. Reason 6. Industry standard. Every major structural engineering program is now implementing Python APIs. Abacus, IDEA Statica, ANSYS, and many more. All can be controlled using Python. These companies aren't doing this because they have nothing better to do. They're doing it because engineers asked for it. They're doing it because Python has become the common language of our industry. When you learn Python, you're not just learning a language, you're learning the key that unlocks your other tools. For instance, this code creates a Lucis model from scratch. This script carries out beam shape optimization in Strand 7, and I'm sure you've seen Python components in Grasshopper. Reason 7. Future-proof. The world is moving towards automation, data-driven design, and parametric modeling. Python is the common language that ties it all together. It's not a passing trend. Python is here to stay. If you want to invest in a skill that will grow with you, open doors now and in the future, Python is the best way to future-proof your career. In this course, I'm going to teach you how to use Python effectively in structural engineering. I'll show you what tools to use, introduce you to Jupyter notebooks, cover the basics, and dive into the most important libraries. If you're done wrestling with spreadsheets and ready to work smarter, follow along and let's get started.